This is going to be the last section in Chapter 8, Statistical Process Control. I'm not going to be introducing any new subjects. Rather, I'm trying to help you to do some review and reflections on things we have learned so far. Eventually, I'm going to show you how control charts can be used to detect the mean shift. Sometimes we don't even know things that we already know can be utilized in a certain way. So this is going to be mostly help you try to connecting the dots. In doing so, we're going to look at a whole new different applications of the statistical process control. But before any discussion, let's do a quick review on this particular problem. Most of you still remember this problem from your homework number 3. The firm firmly believes that their defect rate is 15%. Okay? It also provided the definition of the defects, which by giving you this specification limit. Okay, so I also showed you how to convert this variable measurement into the attribute measurement, right? And we also used the sampling distribution of population proportion to conducting the hypotheses. So the similar problem was also show up in the homework number 4, problem number 2 of the second question. Right? In this case, if you're using the attribute variables, right, you use the normal distribution, average being the hypothesized proportion, and the standard deviation is this quantity right here. So this is the mechanics of doing hypothesis testing. So you first formulate hypothesis here. This is null. This is the alternative. So whatever that the conclusion that you'd like to reach by flipping the existing beliefs, that you put it under the alternative hypothesis, right? Whatever that is existing belief, or the status quo, if nobody challenges, most people believe it is true, these usually goes to the null hypothesis. So in our case, most people believe it is going to be 15% because people said so. Okay, so we're trying to arrive to a different conclusion by flipping the null hypothesis. We also picked 0.05 as our error tolerance. Okay, picked our error tolerance level at 5%, or alpha equal to 0.05. This is very important player in today's section, as a lot of my explanation will be surrounding this value of alpha. Okay, and then distribution wise, we are using this hypothesized distribution with a 15% of mean, standard error being this, right, and the shape is normal. If you look at it, we are only allowing 5% of mistake. Okay, what type of mistake? To be more specifically, we only like to make 5% mistake when we reject the null hypothesis. Okay, in other words, alpha is associated with the rejection. Okay, we're rejecting the null hypothesis. Okay, so let's take a look how this works, right? Because alpha is 5%, we are splitting 2.5 to each end. Okay, so this is, remember, sampling distribution of population proportion. Therefore, this is regarding the sample results. So when you picked a sample that is too small, right, too small or too big, that both will lead to the rejection of the null hypothesis. Okay, because this is your average 15%. Let's say you, in the first draw, your sample average was like 45%, right? It's highly unlikely that the average is 15%. Therefore, we reject the null based on this. Okay, frankly, that's what the hypothesis testing is do. However, there's one thing I'd like to remind you is that theoretically, it is totally possible you can obtain 45% as the sample result, because sample result by its nature follows normal distribution. Think about what normal distributions look like. It extending from the negative infinity all the way to positive infinity. Although it is very rare, although it is going to be really, really rare, but you can expect 45% of sample outcome, even the average is 15%. Okay, but even though you may obtain this type of sample outcome, but if you kind of keep sticking to that type of rhetoric, namely, all things is possible, right? All things are possible. In this case, again, all things are possible. 0% is possible, 100% is possible, because normal distribution extends from the negative infinity all the way to positive infinity. So everything is possible. It's good. Everything is possible. However, if you're sticking to everything is possible type of rhetoric, you will not be able to make any decision. Okay, so that is the reason why we specify alpha equal to 0.05. Okay, 45% still can be obtained when the average is 15%. However, we'd rather make a decision at this point. If it is 45%, we will reject the null hypothesis. Okay, so you are erroneously rejecting the null hypothesis, even though this is from the same distribution. Okay, but we would like to control the frequency of making mistake under 5%. I don't know if this whole thing made sense to you. I wish I can explain it easier, but there are certain things it's just not very easy to explain in simple 1 or 2 sentences. Okay, again, let me summarize nevertheless. The alpha is the cost of making decision. Okay, alpha is cost of making decision. What is the cost? Your mistake is going to be your cost, right? If you do not make any decision, you won't make any cost. Okay, so you make alpha mistake when you reject it. You make a beta mistake when you accept it. So whichever way you're making decision, you are incurring some cost. We'd like to maintain the cost under 5%. Okay, that is the meaning of alpha. So even though the 45% is totally possible, but even it is something possible, we'd still like to reject the null hypothesis. Okay, so that is the kind of the story behind alpha and the rejection of the null hypothesis. So with that in mind, let's move on to the first reflection. Because you know the control limit control chart is actually based on the sampling distribution. Okay, so a lot of the applications on the control limits are following the properties of the sampling distribution. Let's take a look at the first reflection here. Even for the same process, control limits can be different based on the sample size n. Okay, recall this table, this constant table right here. Okay, let's just briefly take a look at how we have constructed X bar and R chart. So you're taking, if you look at here, this is upper control limit and this is our lower control limit. The control limit is actually dependent upon the size of A2. Okay, size of A2. And size of A2 is actually dependent upon the sample size. So for example, our A2 are in this first column. When your sample size is 2, meaning the factor A2 is 1.88. However, if you increase your sample size all the way to 10, size of A2 will suddenly become less than 1/6 of A2 under sample size of 2. Okay, that is what I'm saying. So the control limits can be different based on the sample size, even you are dealing with the same process. Okay, that is the same with the attribute measurement data. So again, this is very clear here, right? This is the margin of error you use to construct the control chart. As you can see, p bar can be constant. However, the n, the sample size, is actually is actually one thing I'm talking here. So when you have a bigger n, this will be much smaller than when you had a smaller n. Okay, therefore, even again, the conclusion is even for the same process, if you're picking larger sample size, the control limit can be narrower. Okay, will narrower control limit more helpful or wider control limit more helpful? Okay, that is the question. You can keep thinking about that. The second reflection is that alpha value can also be seen as the frequency of line stoppage for inspection. Okay, alpha. So if you remember the this example right here, we used alpha as the level of error tolerance. Okay, but here alpha is the same alpha. However, under the quality control context, this is equivalent of the line stoppage. Okay, because according to rule number one, according to rule number one of detecting process out of control, when you spot one point outside of control limit, right? That is a sign of process out of control, that it prompts you to stop the system and do an inspection, right? If we are using alpha equal 0.05 level, this is your control limit. Okay, this is going to be your control limit because it gives you 2.5% above, 2.5 below, and anything outside of these critical value is actually considered as outlier. Okay, so the greater alpha value, the more frequent you have to stop your line for inspection. Okay, again, the conclusion here is alpha value can be seen as the frequency of the line stoppage for the inspection. Every item outside of this limit is considered as outlier that raise some suspicion over the true mean. Okay, that is why. Next slide. You can choose the value of alpha by using different control distance. Okay, here we know that this is 2.5% outside of the limit. Therefore, here z is equal to 1.96. Here z is negative 1.96. Okay, so if we follow the capability index approach, right? Capability index approach, you can see that this is not enough for 3 standard deviation. Okay, this is only 65% of 3 standard deviation. This is exactly 1.96 of 3 standard. This is 1.96 standard deviation. This is almost 2 standard deviation. But if you think about that, this is 65% of 3 standard deviation, right? 3 multiplied 65 is exactly, I think it's around 1.95, but you get the idea. Okay, this is about 2 standard deviation. It means when we use the hypothesis testing step, if we're using alpha equal to 0.05, okay, that means we're using 1.96 control distance to conducting the hypothesis testing. However, if you move on to the control limit application, because a lot of times we're using 3 standard deviation as a control distance, okay, in that case, our alpha will be squeezed to what? If you add this probability and this probability together, the alpha is 0.00270. So under 3 sigma control distance, our alpha is much smaller than 1.96 control distance, which it has alpha value of 5%.